Good morning. This is Alwilan P. Bello from the Bukidnon State University, Malaybalay City, Bukidnon. Today I'm going to share to you the results of our research entitled Experiments in Wave Optics Using Semiconductor Diode Laser. Interference of light waves refers to any situation in which two or more light waves overlap in space. This phenomenon is characterized by the formation of bright and dark fringes that are projected on a screen when light waves passes through single or multiple slits, or what we call the diffraction gratings. So this is the illustration as depicted in figure 1. So you see when there is destructive interference, dark fringes will occur, while for constructive interference, we will observe bright fringes on the screen. So the problem, to observe interference of waves from two light sources, the following conditions must be met. One, the light sources must be coherent. That is, they must maintain a constant pace with respect to each other. And two, the light sources must be monochromatic, that is, they should be of a single wavelength. Now, since an unpolarized natural light, such as sunlight, is propagated in all directions and composed of several frequencies other than a single frequency, it is incoherent and monochromatic. So these properties of unpolarized natural light make it impractical to be used as light source for interference experiments. For the light bulbs have been used as conventional light sources in optic experiments. Now, even though light bulbs radiate monochromatic light in radially outward direction, its light intensity rather decreases by inverse square law at long distances. Laser is an acronym for light amplification by stimulated emission of radiation. There are many types of laser that produce highly coherent and very nearly monochromatic beam of light. The semiconductor laser diode is a type of laser that has many popular applications in modern technology, such as in CD and DVD players, laser printers, fiber optic communication system, anti-burglar alarm system, and many more. So our objective here is A, to develop laser setup with semiconductor diode laser as a light source and to perform interference and polarization of light wave experiments. So these are the specific objectives: to produce interference patterns, to determine the wavelength of the laser beam, to determine the grating distance of the CDR, and to describe the relationship between polarization angle and light intensity, according to Malus law. Okay. For the experimental design under the methodology, the semiconductor diode laser is used as a source of coherent and monochromatic light for experiments in interference and polarization of light waves. Experiments are done in a dark room, and variations in the laser setup are explained in detail in the following subtopics. So this is figure 2, diagram of laser setup for diffraction grating experiments, wherein we have the diode laser here, a diffraction grating in the middle of the setup, and then at some distance there is the screen. Okay, the semiconductor diode laser produces laser beam towards a diffraction grating, and the diffraction grating device produces interference patterns of bright and dark fringes on the screen. Now, the distance L between the diffraction grating and the screen is recorded first before the experiment starts, while the pattern intervals are measured using a meter stick. Here's an actual setup as illustrated in figure 3. Now, we also have a CD diffraction, a CD grating experiment using a CDR as depicted in figure 4. Uh, this one is the actual setup in figure 5. And the polarization of light waves in figure 6, we have the diode laser, a polarizer, another analyzer, and a photodetector connected to a voltmeter. Okay, so a polarizer is placed next to the semiconductor diode laser, and the resulting beam will proceed to the analyzer. The transmitted laser beam is directed to a photodetector, which in turn produces an electrical signal that is proportional to the intensity of the laser beam. And the voltage signal can be measured by the voltmeter in volts. Here is the actual setup. For the results and discussion, we have here the result in figure 8, the interference pattern of laser beam. Okay, diffraction grating experiments had constantly produced a central bright fringe located in the middle of two symmetric sets of bright fringes. Now, in each set of bright fringes, the first bright fringe from the center marks the first order maximum, while the second bright fringe from the center marks the second order maximum, respectively. Here is the scatter plot in figure 9. This is the superimposed Ym versus L graphs of distances y1 and y2, respectively, as obtained from diffraction grating experiments. So we were able to get a regression equation, okay, from figure 11. And for the interference of light waves, again, this one is taken using the CD grating experiment. And again, the central bright fringe is located in the middle of two symmetric sets of bright fringes. And in each set of bright fringes, the first bright fringe from the center marks the first order maximum, so on and so forth. Here is figure 11, the superimposed Ym versus L graphs for the CD grating experiment. And again, we get the regression equation. This is the summary of actual findings for the diffraction grating and the CD grating. Take note that in both experiments, we were able to observe order number M1 and M2. And we got considerable percentage error, not more than 4%. So here we have 2.59% error, 3.12, 1.94, and 3.32%. These are all acceptable in the undergrad laboratory level. For the polarization, we have this sinusoidal scatter plot for the intensity versus the angle. So figure 12, this is the superimposed intensity versus angle graph of actual and predicted values. Another graph also in figure 13. This one is intensity versus cosine squared theta. So as you can see, there is a linearity of the data that we obtain. And from that regression, we were able to get the regression equation, such as intensity is equal to this one, which is actually the slope. No, the y-intercept and the slope. So for the conclusion, diffraction grating experiments had produced characteristic diffraction patterns and bright and dark fringes on the screen. The set of data obtained from diffraction grating experiments were used to deduce experimental value of laser beam wavelength, lambda, within maximum percentage error of 3.12%. Therefore, the utilization of superconductor diode laser as light source made it possible to produce very accurate results due to its coherent and monochromatic laser beam. I think it's also the same with the CD grating experiments. Uh, Due to the coherent and monochromatic laser beam, we were able to get highly accurate results. Okay. Uh, Another one is for the Malus law. There is a very high positive correlation between the density and cosine squared theta variables as predicted by Malus law. For some recommendation, it is recommended to develop and validate an accompanying manual containing the experiments suited for this setup. Here are the references. Thank you for listening.